A fascinating thing with algorithms is that we can't solve the same problem with totally different methods, and it will be the case in this video. We will solve the count sorted vowel strings problem with 3 different solutions. The problem says, given an integer n, return the number of strings of length n that consist only of vowels and are lexicographically sorted. A string s is lexicographically sorted if each character comes before or same as the next one in the alphabet. For example, the string a, e, e, I, u is lexicographically sorted because a comes before e in the alphabet, e comes same as e comes before I, and I comes before u. And we will see 3 methods to solve this problem, one that uses backtracking, one that uses dynamic programming, and one that uses math. So please stay until the end of this video, you'll learn many things today. An intuitive solution is to try all the possibilities and count the ones that respect the condition of being sorted. But when trying possibilities, as soon as we notice that the vowel that we want to add to our string will break the lexicographic order, we don't call the function again, because backtracking leaves possibilities that won't lead us to a valid solution. In our case, a valid solution is a sorted vowel string. You also need to know that at each recursive call we will call the function again at most 5 times, because we have 5 vowels, so we may call once to add the letter A, once to add the letter E, and so on. With n equal to 3, for example, in the recursion tree, we have the initial function call, and from here we can add any vowel we want because the string is actually empty, so we'll make all the 5 recursive calls. But in the next level of the recursion tree, it won't always be the case. With the letter A, we can make the 5 calls because A is lexicographically smaller than or equal to all the vowels. But with the letter E, we can only make 4 calls. We cannot call with the letter A because E is greater than A and the string EA wouldn't be sorted. And with the letter I, we can only make 3 calls. With the letter O, only 2 calls. And with the letter U, only 1 call, the one where we add the letter U itself, because the only vowel that is not smaller than U is U. Basically, you just need to know that when a string is ending with A, we have 5 possibilities, when it's ending with E, we have 4 possibilities, with I 3 possibilities, with O 2 possibilities, and with U 1 possibility. This detail is very important to know. Let's go back to our recursion tree. We still have one level to check. In the last level, the same story will happen. Cases where the last letter is A will call the function 5 times, cases where the last letter is E 4 times, and so on. And it's the last level because n is only 3 in our example, and we got all sorted vowel strings of size 3. To get their number, we just return 1 in the base case and we do the sum. The orange number represents the number returned by that call. In code, our recursive function takes 2 parameters, and the remaining characters that we need to add to our string, and last, the last character that we added to the string to be able to compare with the vowel we want to add to see if adding it will break the order or not. You can see that we are not saving the whole string, we just need their number, so saving only the last character is enough. Inside the function, the base case is when n is equal to 0. It means that we have no more characters to add. We found a sorted vowel string, so we return 1. And in the recursive case, for each vowel, if the last character is smaller than or equal to that vowel, then adding this vowel won't break the order, so we can call the function. N becomes n-1 because the number of remaining characters to add decreases, and the second parameter is the vowel we just added now because it becomes the new last character of the string. You can also notice that we're adding the result to a variable mb because the number of valid strings is the number of valid strings when we add an A, the number of valid strings when we add an E, and so on. This is why we're doing the sum. But the problem is that this solution is very slow. At each call, we're calling the function again up to 5 times, and we're adding 1 character by level only. We get an O5 power n time complexity, which is very inefficient. This is why we'll move to the next solution, the dynamic programming solution. The bottom-up approach of dynamic programming starts by solving the smallest possible subproblems, then keeps solving bigger and bigger ones until it arrives to the one we want to solve. In our case, the smallest subproblem is to count the number of sorted vowel strings of size 1, then to count those of size 2, of size 3, and so on until n. This is why we will use an array of n elements, where the ith element represents the number of valid strings of size I. Let's start. We know that the number of valid strings of size 1 is 5 because we have the string A, the string E, I, O, and U. Now the question is, how can we get the number of strings of size 2 knowing that the number of those of size 1 is 5? How to move to the next result? Because that's what bottom-up dynamic programming is about, always getting the next result starting from results we computed before until reaching the one we're searching for. If there was no condition on strings we are counting, jumping to the next element on the DP array would be very easy. We just need to multiply by 5, because with 5 possible vowels, we have 5 strings of size 1, 25 strings of size 2, 125 strings of size 3, and so on. But here we have a condition, and we don't actually have a formula to move from size I to size I+1. And this is why dynamic programming can be hard sometimes. The general idea remains the same, but applying it on a problem may require extra thinking, which is the case here. The reason why we are not able to jump to the next element is that we don't have enough information. If only we could know the number of strings of each vowel and not the total number. You've guessed it, instead of putting the total number of valid strings of size k, we'll have the number of valid strings of size k that start with A, that start with E, and so on. So instead of having a 1D array, we will have a 2D array of n rows and 5 columns, where each column represents a vowel. So in the first row, instead of having 5, we'll have 1, 1, 1, 1, 1, because with the size 1, we have one string that starts with A, one string that starts with E, and so on. Okay, but how to fill the remaining rows? Here are our strings of size 1. Let's count the ones whom we can add A from the beginning without breaking the order. We can do it for all of them, we put 5 here. With the letter E, we can do it for all of them except A, we put 4 here. With the letter I, we can do it for I, O, and U, we put 3. With the letter O, we can do it for O and U, we put 2. And with the letter U, we can do it for U only, we put 1. Next row, with the letter A, we can put it before any string, so we just do the sum. 5 plus 4 plus 3 plus 2 plus 1 is 15. With the letter E, we cannot put it before a string that ends with A, but we can with remaining ones, so the number is 4 plus 3 plus 2 plus 1, which is 10. With the letter I, we can put it before strings that end with I, O, or U, and 3 plus 2 plus 1 is 6. With the letter O, we can put it before strings that end with O or U, and with the letter U, it can come only before the letter U, we put 1. Here we started noticing a pattern, is that the strings of size k that start with the letter A are the strings of size k-1 that start with the letter A, E, I, O, or U. The strings of size k that start with the letter E are the strings of size k-1 that start with the letter E, I, O, or U. The strings of size k that start with the letter I are the strings of size k-1 that start with the letter I, O, or U. The strings of size k that start with the letter O are the strings of size k-1 that start with the letter O or U. And the strings of size k that start with the letter U are the strings of size k-1 that start with the letter U. And this is how we're solving our problem by using dynamic programming. The number of strings of size k that start with the vowel V are the sum of strings of size k-1 with whom we can add the vowel V from the beginning without breaking the order. Please take some seconds to read this sentence again. So if we follow this logic, this is how the DP matrix will get filled. Now we have the number of strings of size n with each vowel, we just do the sum and we get our output. And this is why I told you that dynamic programming can be tricky sometimes. We had to think of this logic to continue filling the DP matrix. In code, we create a matrix DP which has n rows and 5 columns. We fill the first row with ones and we can start filling remaining rows. A is accepted by all the vowels, so it's the sum of all the previous row. We write dp of I0 is equal to dp of I-1 0 plus dp of I-1 1 plus dp of I-1 2 plus dp of I-1 3 plus dp of I-1 4. E is accepted by E, I, O, and U, so we write dp of I1 is equal to dp of I-1 1 plus dp of I-1 2 plus dp of I-1 3 plus dp of I-1 4. I is accepted by I, O, and U, so we write dp of I2 is equal to dp of I-1 2 plus dp of I-1 3 plus dp of I-1 4. O is accepted by O and U, so we write dp of I3 is equal to dp of I-1 3 plus dp of I-1 4. and u is accepted by u only, so we write dp of I4 is equal to dp of I minus 1, 4. And after filling the whole matrix, the last row contains the number of sorted vowel strings, those that start with A, with E, with I, with O, and with U, so we just return the sum. And this solution has an O of n time complexity, which is way better than O of 5 power n of the first solution. Now, what if I tell you that we have a mathematical formula to directly find the number of sorted vowel strings without doing all what we've done here? In combinatorics, we have combinations and permutations, and for each one of them, we have without repetition and with repetition. Let me show you an example. We have these 5 balls and we want to form a group of 3 balls. To form a combination without repetition, we just take a first ball, then a second one, then a third one. And you can see that once we take a ball, we cannot take it again. The possibility is gone. This is why we have a combination without repetition. But when making combinations with possible repetitions, once we take a ball, we don't remove the possibility of taking it again. So we can, for example, take the red ball, take the blue ball, and take the red ball again. With permutations without repetition, we take a first ball, then a second one, then a third one, without being able to repeat. But the difference with combination is that here the order is important. Here we took red, blue, green in that order, but if we took, for example, blue, red, green, we would get another permutation. Which is not the case with combinations. This one and this one are considered as the same combination. The important is that they contain the same elements. The order is not important. And for permutations with repetition, it just means that we can take the same element many times. For example, red, blue, red. But the order is still important. Red, red, blue, for example, is a different permutation. You can imagine the difference between permutations and combinations as the difference between arrays and sets. This array and this array are not equal because even if they are made with the same elements, but they are not in the right order, the comparison returns false. There are 2 different permutations. But this set and this set are equal. They are made of the same elements. Even if not in the right order, the comparison returns true. They are considered as the same combination of elements. Okay, but what does all this have to do with our problem? In reality, to form a vowel string of size n, we're taking n vowels from our 5 vowels with repetition. And we're searching for the number of combinations with repetition, so we will apply this formula. But before doing so, why combinations and not permutations? If there was no condition on strings we're searching for, we would use permutations. Because the order is important in strings, this one is not equal to this one, even if they're made with the same characters. But here we're counting only sorted ones, and you need to know that given n vowels, even if with repetition, we can only make one sorted vowel string. For example, if we have 2 A's, 1 E, and 1 U, we can make a lot of strings, but only one of them is sorted, the string AAEU. So all of these strings belong to the same sorted string. This is why we have to count this group of vowels only once. And to count the number of combinations without repetitions, we have this formula, where n represents the number of elements in the set from where we choose and r the size of the combination. In our case, n is 5 because we have 5 vowels, and r is n because we're making strings of size n, so we're choosing n vowels from a set of 5 vowels. And it's not a problem if n is greater than 5 because our combinations can contain repetitions. After replacing in the formula, we got n plus 4 factorial divided by n factorial times 4 factorial. N plus 4 factorial is n plus 4 times n plus 3 times n plus 2 times n plus 1 times n factorial. We replace and we can remove these 2 terms and this is what we get. 4 factorial is 24 and we got our formula. So in code, we just return n plus 4 times n plus 3 times n plus 2 times n plus 1 divided by 24. And if we assume that multiplication and division have an O of 1 time complexity, then the solution has an O of 1 time complexity thanks to mathematics. Before ending this video, I want to talk about something in the first 2 solutions. In the dynamic programming solution, we couldn't directly jump from a cell to the next one because we didn't have the formula. But now we do, the one we found now. We know that the number of valid strings of size k is k plus 4 times k plus 3 times k plus 2 times k plus 1 divided by 24. What we can do is to find the ratio between the number of valid strings of size k and of size k plus 1 to be able to multiply. By putting k plus 1, we get this formula. Now we divide by the number of strings of size k to get the ratio, and we get k plus 5 divided by k plus 1. It means that if we know the number of strings of size k, we have to multiply by k plus 5 divided by k plus 1 to get the number of those of size k plus 1. And we can fill the array this way. We start with 5 because we have 5 valid strings of size 1, then we keep multiplying to move to the next cell. We get 15, 35, 70 and so on until filling the whole array. The output will be in the last cell. But we don't need to do this now, because we already have the final formula. It was just to show you that we could fill the initial DP array if we knew the ratio. And about the first solution, I wanted to precise something about the time complexity. We said that the time complexity of the first solution is O 5 power n because each call can recursively call the function at most 5 times. But there is a difference between 5 times and at most 5 times. Let's count the number of recursive calls. Each call in the last level of the recursion tree represents one valid string of size n, and we know their number. The level before it represents valid strings of size n-1, and we can find their number by replacing n with n-1 in the formula. And so on until 0, so the number of recursive calls is the number of valid strings of size 0, of size 1, and so on until n. And we have the formula of the number of strings of size k, so we can do the sum. The number of recursive calls is the sum of k plus 4 times k plus 3 times k plus 2 times k plus 1 divided by 24, where k goes from 0 to n. By using Wolfram alpha, we get this formula, which is equal to this one after simplifying. We have this number of recursive calls, and each one of them has an O of 1 time cost. So we just remove smaller terms, we remove the constant, and we get an O of n power 5 time complexity, and not O of 5 power n as said before. I know that O of n power 5 is still slow, but it was to show you that to find the time complexity of a backtracking algorithm, it's important to know the number of recursive calls to find the tight upper bound. Here, by knowing the number of recursive calls, we found out that the tight upper bound is n power 5 and not 5 power n, and n power 5 is way smaller. We reached the end of this video. If we had to describe the 3 solutions we used to solve this problem, the first one would be try all the possibilities where the new vowel doesn't break the order, and if n reaches 0, add 1. The second one would be the number of strings of size I that start with the vowel v are the sum of strings of size i-1 with whom we can add the vowel v from the beginning without breaking the order. The third one would be the number of sorted vowel strings is the number of combinations with repetition of n vowels taken from 5 vowels. I know that this lecture was a little bit difficult, but I hope that you understood the logic behind the 3 solutions. Ask me in comments if you didn't. See you in the next one.